Good morning. It's March 14th, and this is your daily brief in science. Here's everything you need to know. A recent breakthrough in material science has emerged from the Chinese Academy of Sciences, where researcher Luojun Du and his team have developed a technique to produce atomically thin layers of metals. This method was previously considered impossible, but it now opens new avenues for advanced research and applications. The innovative process utilizes flat sapphire crystals in combination with a layer of molybdenum disulfide, or MoS2, to compress powdered metals under high temperatures and pressures. Drawing inspiration from traditional copper forging methods, the researchers employed a hydraulic press to create thin metal sheets with remarkable precision. The team has successfully produced large sheets of metals with sub-nanometer thickness and diameters exceeding 0.1 millimeters, allowing for detailed studies of their unique properties. Remarkably, these sheets can be as thin as 2 atoms, which could lead to significant advancements in fields such as industrial chemistry, optics, and computing. These two-dimensional metals exhibit unique characteristics that may enhance research into quantum phenomena and superconductivity, as well as contribute to the development of ultra-low-power transistors and transparent displays. Du explained that despite the seemingly simple process, new techniques were necessary due to the thermodynamic instability of freestanding metal atoms. Previous efforts to create ultra-thin metal sheets faced significant challenges, particularly with oxidation when exposed to air. One remaining challenge is the removal of the MoS2 layer, which could impact some applications. However, initial findings indicate that it does not affect the electrical conductivity of the metals. The properties of these two-dimensional materials differ significantly from their bulk counterparts, with graphene being a well-known example of an atomically thin layer of carbon. This breakthrough was reported in the journal Nature on March 12, 2025, and has been likened to the creation of graphene. Experts, including Javier Sanchez-Yamagishi from the University of California, Irvine, have underscored the importance of this development as a foundation for further research into these novel metal sheets. A new study published in Nature Astronomy has upended previous beliefs about the origins of long-period radio transients. Researchers, led by Iris de Ruyter from the University of Sydney, have discovered that these emissions actually come from a binary star system, rather than neutron stars as previously thought. The system, designated ILTJ 1101 plus 5521, is located approximately 1,600 light-years from Earth and features a red dwarf and a white dwarf in synchronized orbits, completing a cycle every 125.5 minutes. The signals emitted from ILTJ 1101 plus 5521 occur at regular intervals of 125.5 minutes, lasting about 1 minute each. This duration distinguishes them from fast radio bursts, which last only milliseconds and are much more powerful. The emissions from this binary system are of lower energy and have a longer duration, suggesting a different source of radioactivity. Detailed spectroscopic analysis revealed rapid movement of the red dwarf, indicating a gravitational interaction with the white dwarf, which is too faint to be observed directly. The close proximity of the two stars leads to their magnetic fields colliding, generating detectable bursts of radio waves. These findings emphasize the need for further exploration of long-period transients to understand their origins and mechanisms more fully. Future research will focus on high-energy ultraviolet emissions from ILTJ 1101 plus 5521 to gain deeper insights into this binary system. De Ruyter developed a new detection technique that enabled the discovery of these radio pulses, first detected in archival data from the LOFAR radio telescope. The earliest detection dates back to 2015, with subsequent observations confirming the system's unique characteristics, including photometry measurements indicating an excess of blue light from the system, supporting the presence of the white dwarf as the source of the radio emissions. A recent study sheds light on the role of the epipharynx in long COVID, particularly examining the activation of SARS-CoV-2 signaling pathways and the potential benefits of a new treatment called epipharyngeal abrasive therapy, or EAT. Long COVID continues to affect many individuals, manifesting symptoms such as chronic fatigue and cough long after their initial recovery from COVID-19. Chronic epipharyngitis may exacerbate these symptoms, prompting researchers to investigate the epipharynx, which is rich in proteins that facilitate SARS-CoV-2 entry and plays a significant role in chronic inflammation. ET, developed in Japan, is an outpatient treatment that involves nebulizing the inflamed epipharynx with a zinc chloride solution aimed at reducing inflammation and alleviating symptoms. In the study, 3 long COVID patients underwent EAT, receiving weekly treatments over 3 months, which led to significant improvements in their symptoms and reduced inflammation scores. Histological examinations revealed notable improvements in the inflamed ciliated epithelium, and levels of pro-inflammatory cytokines showed significant declines, indicating the anti-inflammatory effects of EAT. Furthermore, EEAT was associated with decreased levels of residual SARS-CoV-2 RNA in the epipharynx of most patients, suggesting a potential mechanism for symptom relief. Post-treatment assessments indicated significant reductions in viral RNA and symptom relief, measured by the visual analog scale, highlighting the effectiveness of EAT. The treatment was shown to suppress T-cell receptor signaling pathways and reduce the expression of inflammatory cytokines such as IL-6 and TNF-alpha, which are linked to long COVID symptoms. Using Visium HD technology, the study provided high-resolution insights into gene expression changes in the epipharynx, revealing ongoing immune response activation in patients even after the acute infection had resolved. Gene expression analyses demonstrated that B cells and plasmacytoid dendritic cells in the epipharynx exhibited heightened immune responses, indicating chronic inflammation and immune activation. Future research with a larger sample size is necessary to further validate the effectiveness of EAT and comprehensively explore its impact on long COVID symptoms. China is set to launch its ambitious Tianwen-3 mission to Mars in late 2028, aiming to be the first mission to retrieve samples from the planet. This mission is inviting international collaboration for scientific projects, highlighting its significance in the global space exploration landscape. Tianwen-3 will target 3 pre-selected landing sites: Amazonas Planitia, Utopia Planitia, and Chrysoplanitia. These locations were chosen for their potential to preserve biosignatures, which are critical in the search for past life on Mars. The mission will employ advanced sampling strategies, including surface sampling and drilling, to focus on areas likely to contain preserved organics. To support these efforts, Tianwen-3 will utilize sophisticated instruments such as a Mars subsurface penetrating radar and a Raman and fluorescence analyzer, aimed at studying the Martian subsurface and searching for organic materials. The primary goal of Tianwen-3 is to collect and return samples from Mars, specifically targeting the detection of potential biosignatures to explore whether life ever existed on the planet. A successful mission could significantly enhance China's status in space exploration and provide crucial insights into the existence of life on Mars. This initiative also builds on China's previous successes in lunar sample returns, further enhancing its capabilities in planetary exploration. The China National Space Administration issued an invitation for international collaboration on March 13, 2025, amid challenges faced by NASA, including leadership changes and budget cuts. Proposals for collaboration must align with Tianwen-3's scientific objectives, which include searching for signs of past life. CNSA is offering 15 kilograms of mass for international projects on the Earth Return Orbiter and an additional 5 kilograms on the Mars Orbiter. Interested teams are required to submit expressions of interest by June 30, 2025, with final selection of payloads set for October 2025. Delivery of flight models will be required by 2027, and the selection process for international projects will be expedited with letters of intent due by June 2025. A groundbreaking study from King's College London reveals a potential new avenue for treating treatment-resistant breast and ovarian cancers. Researchers have found that IgE antibody therapy could effectively shrink tumors that do not respond to existing treatments. Published in the Journal for Immunotherapy of Cancer, the study indicates that IgE antibodies can stimulate the immune system against HER2 positive tumors, which are known for their resistance to current therapies. Led by Dr. Heather Bax, the research focused on engineering IgE versions of IgG therapies to enhance immune cell activation against HER2-expressing cancer cells. The study explores how IgE antibodies engage immune cells within the tumor microenvironment, potentially improving efficacy against solid tumors. HER2-positive cancers are typically managed with IgG-based therapies like trastuzumab, commonly known as Herceptin, and pertuzumab, but many patients develop resistance to these treatments. In experiments with mouse models of trastuzumab-resistant HER2-positive tumors, IgE therapy significantly slowed tumor growth. It also increased the presence of activated T cells while reducing the number of immunosuppressive cells. Co-author Professor Sofia Karagiannis noted that IgE antibodies have shown consistent effectiveness against challenging solid tumors, suggesting a promising new class of cancer drugs. She further emphasized that IgE antibodies activate the human immune system to restrict cancer growth across various tumor types. Researchers believe, with further development, that IgE therapies could be available for human use within the next 3 to 5 years, pending clinical trials and additional studies. This has been your daily brief in science. To read more about these stories, follow the links in the episode bio. You can also subscribe to these updates via email at www.brief.news. For more daily podcasts about the topics you love, visit brief.news/podcasts. We'll be back Monday with everything you need to know.